Okay, welcome back. So we'll get started again with part 2 of EIC Accelerator Physics. So Christoph, all set. Then you have the
Right. Yes.
yeah. Right.
Okay. So I want to talk about. Okay, this way. All right. So I will continue the accelerator physics talk that Sergey started yesterday. So I hope we coordinated more or less that I pick you up at the right point, that I'm not losing you on the first slide. So I do a first little bit of a recap, what you hopefully learned from Sergey yesterday. And then we apply all that to the point of the machine where you hopefully are most interested, or you're interested at all. That's the interaction region. So we go over things like luminosity, focusing, beam separation, crab crossing, luminosity limitations, transport of low PT particles through the interaction region, and then polarized beams and a summary. Okay, so I hope you have learned this so far, that linear motion of particles in accelerators is described by transfer matrices. It's linear, so obviously you remember there was something like linear algebra in first semester or so. In the second, and that's a linear transformation. So that's why linear motion of particles you can describe by matrices. That's what your linear algebra dealt with in that semester. And this is here just an example of the matrix for a quadrupole. So it describes motion in the horizontal plane X and the vertical plane Y. X prime and Y prime are the angles of the particle trajectory relative to the design orbit, basically. So I can also think of that as basically PT divided by the longitudinal momentum. So it's an angle. You see here, that's a cross-section of a quadrupole with these 4 poles, or south-north, south-north. And as a result here, what happens if you send a particle, a charged particle through a quadrupole? Of course, the motion is governed by the Lorentz force. And if you look at these poles here, it turns out that in one plane, your particle will be defocused, it will be pushed away from the center of the quadrupole. In the other plane, it will be focused, it will be pushed towards the center of the quadrupole. So you have to build an optics that focuses overall in both planes, because you want to keep your beam together. So Sergey showed you that yesterday. I went over the slides, so I guess to that point. So the most simple arrangement of magnets there to do that is a photocell where you alternate magnets that are horizontally focusing with magnets that are vertically focusing. And you have drifts in between, of course. And that focuses overall in both planes. The other linear element that you have is a dipole. So in this case here, it's a horizontally bending dipole. So you have a vertical magnetic field in this thing. And then the horizontal motion in that dipole relative to the closed orbit. So this is not in real space. That's relative to the curved orbit, the design orbit in that dipole, described here by this part of the matrix, the first 4 elements here. Vertically, it's just a drift of length z in this case. So basically, when you look at this matrix, you also automatically have the matrix for a simple drift section, where just an angle, an orbit angle x prime just translates into an offset at the end of the drift. That's all that means. Okay, then you have learned how to describe the beam, the transport of an entire beam as an ensemble through a focusing channel in an accelerator. So the beam is, so here that is described by what we call twist parameters. So you have the beta function that should ring a bell, hopefully. You heard the expression yesterday, I hope. And then you have its derivative alpha, and then there's gamma there, which is just compound of alpha and beta. And then you can define a beta matrix here with these three, with beta, alpha, and y at every location. And that beta matrix gets transformed through your accelerator using the same transport matrices that I showed you here in this first slide for each element. So you start with your starting values for beta and alpha. Gamma, of course, is just derived from these two. It's only two parameters. And then you can transform your beta function through the accelerator. Okay, another important thing that we have to introduce here, or at least repeat here, that is the phase space ellipse. So this is here the phase space ellipse, let's say that's in the horizontal plane, so x prime, right? The axes here are labeled with u and u prime because in the vertical it's the same. So every particle in phase space travels on this phase space ellipse. This ellipse gets transformed through the machine. It doesn't look exactly the same everywhere in the machine. You go through a quadrupole and it gets tilted, for example. But it's always described by its local beta functions and alpha, and epsilon is the emittance. That's a property of the beam itself. So that's the amplitude, basically, the size of the ellipse, you would say. So it's a scaling parameter in that sense. And so with these parameters, you can calculate then the size of your beam, the RMS size. So the RMS size is the square root of your emittance times the local beta function. And then, of course, there is an RMS opening angle, a divergence angle of your beam at every location. And that is described down here. What's important also later when I talk about the interaction region is that these ellipses do not intersect. So if you have an ellipse or a smaller emittance epsilon, then it's just the same shape and it's just nice in here, or if it's a larger epsilon, it's outside, they don't intersect, they have the same shape at every location. And that is important when it comes to detecting particles with Roman pots. Okay, and then we have dispersion. So far I only talked about particles that have the design longitudinal momentum. However, in the beam you also have a small distribution of momenta, or that typically your delta P over P is something like 10 to minus 3 or so. And so that has an impact, of course, on your particle trajectory. It's very simple. You go through a dipole and you don't have the design momentum. So if your momentum is larger than your design momentum, then your dipole deflects you less than it should. And if it's smaller, then it gets deflected more. So that a dipole does something there, and that is described, and the resulting orbit that you get through the machine, the resulting closed orbit for a particle with a delta P over P of 1. So the momentum is off by factor 2, right? That is called the dispersion function, which is nothing but the trajectory around the machine. So in matrix form, this can be written like this. So you have the dispersion and its derivative at any location in the beam. And then you have this transport matrix here through a dipole. And this is the initial values for your dispersion and your dispersion prime. Okay, so to add the longitudinal motion to any of these transport matrices that I showed you in the beginning, we just add the fifth row and the fifth column to the 4x4 matrix. So that's here. These are the same things that you saw before. And for quadrupoles and drifts, there's just this. I just put a 1 down here. So these elements here are the regular. This 4x4 matrix is the regular matrix that you saw before for a quadrupole. So that's all that needs to be done to describe that. So now, what else happens if you have a particle with a momentum offset? Well, the momentum offset messes up your focusing. right? You go through a quadrupole, and again, if you have a longitudinal momentum that does not match your design momentum, you get more or less focusing in that quadrupole. So that's basically, you have the same thing with regular conventional optics, of course. If you have a lens, a glass lens, you send light through that, then of course, depending on the wavelength of your light, which is energy, you get more or less focusing. So you have errors there. Okay, so we have to correct these errors. And how do we do that? So we see here, beam is coming from the left, parallel beam. We have a lens here, and blue here, of course, as usual, that's a particle with higher energy than it should have. Red is less energy. So the focus here changes, and I want to correct that. So the trick is now when I go to a location where I have non-zero dispersion. So dispersion, again, is the trajectory of a particle with an energy offset or momentum offset, longitudinal. So typically, the particle with a larger momentum in a storage ring travels further outside because it has a larger momentum. So the dispersion sorts these particles basically relative to their longitudinal momentum. And what I then do, I place a magnet there that is basically a position-dependent quadrupole. So I want to, since the particle further outside has a larger momentum, it has experienced less focusing in the quadrupoles, I want to give it more focusing. So I want to give it I want to correct this focusing error. So I put a focusing quadrupole in principle on the outside there. So I get more focusing, I compensate for that, and I put a defocusing quadrupole on the inside. And in reality, that is done by a sextupole. So you see that here, the magnet, instead of 4 poles, you have 6. So that is, in fact, then a position-dependent quadrupole. So you get your position-dependent focusing. What happens then is these sextupoles are nonlinear elements. So I can't describe them by matrices anymore, and I get nonlinear dynamics. Nonlinear dynamics at some point leads to chaos and all kinds of funny things. So what happens here, this is a phase space plot here. So this is again x and x prime. And at low amplitudes in this phase space, I get an ellipse, right? This is nice, and then it gets distorted. And depending on my actual setting of my machine, I could say I get this triangular form here. And at some point, for large particle amplitudes, the motion is no longer stable. I lose those particles. So that what we call this here, this outer trajectory, that's what we call dynamic aperture. It's very important in the machine. So it's basically, it has the same function as if you had a collimator there. You cannot have particles stably moving outside this trajectory here. So it limits my available space in the machine. Just want to add here that also nonlinear multipole errors in any magnets, which are unavoidable, they also impact the dynamic aperture. So it's not only sextupoles that do that, it's all kinds of higher order multipoles as well, but they are typically only as real errors in the machine. They are small, so their impact is typically not very large. Okay, so now we tie it all together with the interaction region. So this is here the EIC interaction region. I assume you have seen this plot already yesterday. So we have the hadrons coming from the left, electrons coming from the right. And so we have focusing elements here. This is the central detector in green. And the hadrons go out this way. The electrons come from here. As they get focused in these magnets here, they radiate photons. That's what electrons do when you accelerate them. So focusing is acceleration. And these photons, they are pretty hard, so they can have tens of kilovolts from the from those electrons that are at large amplitudes in the beam. They sample large magnetic fields in the focusing elements. So I have to get them safely through the detector. Otherwise, I create background in the machine. And here for the hadrons, this is the what we call the forward side here. This yellow thing, that's a cone of neutral particles that gets detected here at the 0-degree calorimeter. So I have to provide magnet apertures that are large enough to transport this yellow cone here to this detector. And you can see here, so these boxes here, they show the magnet apertures. It's not the outside of the magnet, it's the inside. And you can see here that these apertures are much larger than I would need for the actual beam, right? I have this cone here and I have to get that through here. And the same here for the electrons. The beam is tiny compared to the synchrotron radiation fan. Okay. So the first parameter you want in any machine is luminosity as much as possible, of course. The higher the better. Luminosity is proportional to the collision frequency, to the numbers of particles in the two rings, and inversely proportional to the cross section. So in other words, this is just number of particles per time and cross section. That is luminosity. So to maximize that, I can maximize my collision frequency, here F. So it's typically, or we can get to something like 100 megahertz. So we have a bunch pattern of 100 megahertz. It's 10 nanoseconds between bunches or 3 meters. So it's pretty packed in this machine with bunches. And that is limited by the kicker rise time. So I have to get my bunches into the machine and I want to get them in there one by one without disturbing the others. So I need a fast magnet that only kicks one bunch in there at a time. It's also limited by parasitic collisions. So if I have an interaction region, I only want particles or bunches to collide in the center of the detector. I don't want them to collide further out where the next bunch is. So if my bunches are, as I said, 3 meters apart in both rings, and I collide these two beams, then I have a parasitic crossing at 1.5 meters, at 1/2 the bunch spacing. And I don't want that. You don't want any events coming from 1.5 meters down or up the beam line. So that's basically the limitation, and that's why I will come to that. That's why we have crossing angle at the end. I also want to maximize particles per bunch, of course. I want to pack as many electrons and hadrons in the two bunches as possible. That is limited by the sources. I just can't generate more polarized protons or more polarized electrons in this tiny space, which is tiny time, of course. And there's also space charge. So that's especially for hadrons. Space charge means if you have a bunch or beam of hadrons, that means you have particles that all have the same charge, right? And they repel each other. On the other hand, they are also traveling, so they are parallel currents. And the net force there that goes with 1 over gamma squared. So the higher the energy, the less important space charge becomes. That's why for electrons, we typically don't have to worry because they have a gamma of 10 to the 4th or so. While for hadrons, we are more like at 100. There are also collective effects. So the beam interacts with its environment, basically. It travels through the beam pipe, and then you have the image charges moving through the beam pipe. The beam interacts with those, and you can that can lead to effects that one bunch excites what we call a wake field in the beam pipe. So the next bunch sees that and then that leads to an instability because you couple all your bunches together through these wake fields. Typically, currents are limited to a few amps. So if you think about it, a few amps of free electrons traveling in the machine. That's a substantial thing. And then, of course, we want to minimize the beam size at the IP. Of course, you want to minimize the cross-section. And what we have there in the EIC is something like 100 micrometers horizontally. It's the RMS size, and 10 micrometers vertically. That is limited by the whole focusing process at the interaction region, and especially by the magnets. It's sort of a technological limit. It's also limited by the chromaticity. If I have these large magnets with a large aperture, and we have a large beam size in them, and large beta, basically, as I will show, that contributes a lot to chromaticity. I have to correct that. I need stronger sextupoles elsewhere in the machine. Strong sextupoles, again, are strong nonlinear elements, so my motion becomes less stable, and that limits this dynamic aperture thing that I talked about before. And last but not least, there's also a limitation then for this beam size. That's basically a limitation on the achievable emittance. That is by IBS intra-beam scattering. So all the particles, as they move around in a bunch, they go through these focusing elements. So the focusing elements, they kick them transversely. That means they pass by each other inside the bunch and scatter off each other. That's a heating mechanism that leads to emittance growth. So there's a limitation, of course, if my emittance grows very fast and I get a large peak luminosity, and after 10 minutes, I have nothing because my emittance is blown away. So these are the limitations there on the luminosity. So now IR focusing. Yes.
That many particles per bunch, can you get multiple collisions per bunch crossing? Like,
yes,
yeah, you can.
absolutely.
Okay.
Yes, you can have multiple collisions, multiple particle collisions per bunch crossing. Yes.
Okay. But an event,
that can become a problem for the detector.
right? Yeah, because an event is defined as just one collision, right?
Yeah. Okay, so IR focusing at the interaction point in the center, the beta function has no slope, it's a symmetry point, so alpha equals 0. Then we use this beta matrix that I showed you, and we also remember how to transform this beta matrix away from the interaction point to the first quadrupole. It's just a drift, so we plug in these matrices here and solve that, and it turns out that the beta function, as you walk away from the center there, from the interaction point, grows quadratically with your distance from the IP. So it grows dramatically if you have something like tens of centimeters of beta function at the IP, and then you go 5 meters away, you get beta functions of hundreds of meters. So it's a rapid growth. Okay. Yeah, so that means, of course, it gets large at the first quadrupole, and as I show it here in this little cartoon, so here you have an interaction point with 5 micrometers, and it grows rapidly. You have to squeeze this beam into quadrupoles. You have to be able to focus that. That means you need large apertures for the quadrupoles, and the required gradient of an IR quadrupole is largely independent of the beta that you achieve at the IP. So you don't really, it doesn't get reduced. The gradient does not get reduced if you relax your beta and make your beam larger at the IP. All that happens is that the beam gets smaller here, and you can make your magnet smaller until it works, right? So a reasonable limit here for the, keep pushing the wrong button. A reasonable limit here for the pole tip field at the aperture here of the magnet, of the superconducting magnet, is about 6 Tesla. So then that gives you then the gradient that you can achieve. Okay, and I talked about the effect on the chromaticity and so on, and that you need larger sextupoles which reduce the dynamic aperture. All right, now beam separation. So the two beams in the EIC, they have vastly different energies, right? You have, let's say 10 GeV electrons and 275 GeV protons. You can't send them through the same focusing channels. If you send the protons through the electron focusing channel, they don't really care much. They get a little bit of focusing, but I mean, it's a factor of 25, right? So nothing really happens there. You can't benefit from that practically. On the other hand, you send the electrons to the proton focusing channel, they get overfocused and they get lost. So you have to separate your beams close to the IP into their respective focusing channels. And you have to do that close to the IP because it's exactly of what I just showed you before. The beta function grows as you get away from the IP. So if you separate too far away from the interaction point, your beta function gets so large that again, you can't build your magnets. So you have to make your crossing angle large enough that the focusing elements for electrons and protons can sit next to each other instead of focusing the electrons first and the hadrons then behind the electron focusing channel, because that would push those several meters away again. The problem, of course, of the crossing angle is that it reduces the overlap between the two beams, and that reduces your luminosity. So you have these two skinny guys here. So this is basically the Rick situation. The electron beam is much shorter than a hadron beam typically, but concept is the same. So a particle that's here in this red slice here of this blue beam only has a chance to collide with the particle in the red slice in the yellow beam if they collide at a crossing angle. If they collide head on, every particle in one beam in principle has a chance to collide with every particle in the other beam. That's how you get your luminosities. This is a severe reduction in your luminosity if you collide at a crossing angle. And of course, this is just a cartoon. In reality, the aspect ratio here of the beam of longitudinal to transverse is much worse. As I said, it's depending whether you look horizontally or vertical, it's, let's say, maybe 100 microns wide, and this beam here is 10 centimeters long. So there's really the slice here that can collide with the opposite beam is really tiny. And you get without doing anything, we would get a luminosity reduction of about 2 orders of magnitude by just colliding at 25 milliradian, which is not a big angle. It looks big here because the scales are distorted if you look closely. Okay, so the trick is here, that's the only movie I have. I usually hate movies and presentations because they are very distracting, I think. So the trick is here that we apply what we call trap crossing. So we have the two beams coming in here, the electrons and the hadrons. And of course, the bunches, they are aligned with the orbit, with the trajectory. And now I kick them here. I grab them. So I kick the head of the bunch down here, tail of the bunch up. Top view, of course, but I'm still staying up and down. So they tumble around, and when they reach the interaction point where they collide, they are suddenly lined up. You can also see that they move transversely as they collide, right? So that has to be taken into account a little bit in the detector analysis to really get the actual interaction point where things happens. But that is a way to get the luminosity back. So here's the overlap between the two, and it reaches nearly 100%. I'm not sure if it does actually reach 100%. Maybe that is just some aliasing that was here there the last little bit. Okay, we also need to do this not only to restore the luminosity, but also for beam dynamics purposes. The beam dynamics would not be stable without grabbing the beams, without these funny rotations here. Okay. So the next luminosity limitation, that's the beam-beam interaction itself. It's essentially similar to the space charge, what I talked about, except now we have beams in two directions, and in this case here with opposite charges, but the opposite charge does not really help you in this sense. You can't take advantage of the factor 1 over gamma squared that you have in space charge. So you really get a force here. It's a highly nonlinear force. This is here the force on a particle if both beams are round. It gets much more complicated, this formula. If you have flat beams, if the vertical beam size is not equal to the horizontal beam size. But here you can see, so this is R is your radial amplitude, your radial position of the particle relative to the center of the bunch here. And you can see you have this exponential factor here, which if you expand this in a Taylor expansion, then you see that your first element here would become equivalent to a quadrupole. So in the center of the beam for small amplitudes, you have a linear force here, and then it turns around at very large amplitudes. It's vanishing, of course, because you are outside the oncoming bunch. And in between, this is the interesting part where it's very highly nonlinear. And we have to take care of that the particle motion in the machine is still stable with this large nonlinearity. So what happens is you have a amplitude-dependent focusing due to this force. If you have amplitude-dependent focusing in a machine, it changes what we call the tune of the machine. And we have to make sure that this tune spread, it's depending on amplitude, does not exceed certain values. Otherwise, again, we can't find a way to operate the machine, and we would lose these particles. Okay, now synchrotron radiation power. I touched on that at some point when I talked about the interaction region of the synchrotron radiation fan that's generated there by the quadrupoles. So accelerated particles, they do emit photons, and in a synchrotron, so in a circular accelerator, they are radially accelerated, and due to the large velocity, the synchrotron radiation is emitted in a forward cone. What is interesting here is that the radiated power scales with gamma to the fourth power. So it scales with energy to the fourth power. It's a lot of power for our machine. So for our 18 GeV, or also for the 10 GeV, because we changed the intensity of the beam in the EIC, we emit 9 megawatts of radiation of photons in this machine. While for the protons, basically nothing happens here. Because at 255 GeV, gamma is only 300. So that's totally negligible. In the LHC, they have synchrotron radiation with their protons, and I believe the damping time is hours in that thing, but at least they see it, so we don't see anything. They are way too low with that. Okay, so now transport of low ET particles. So in your interaction point, you generate particles or you scatter particles. They get a low transverse momentum, and you want to detect them. You can't detect them in a central detector because that transverse momentum is way too small to be detected there. Otherwise, you can't get the beam out of your detector. So you have to do it along the beam pipe. That's with these Roman pots that some of you may be familiar with. And so how that works is basically, so particles are scattered, they receive a transverse momentum. That's how you describe it. We describe that as an angle, right? That's the XDS at the IP. And what happens now, if you consider that in phase space, you have a particle that is traveling on this ellipse here, and now at the IP it gets a kick. So it gets a vertical kick along the X prime axis. It's an angle, and then it travels on a larger ellipse. But ellipses do not intersect. Remember that. So if I want to detect this particle, I can only detect it along this axis here. So I can detect it here, in this case with this tilted ellipse, or here. And I have to make sure that it's actually outside my beam. So what happens is, of course, if I want to detect, or the parameter the only parameter that I have is my beam emittance, right? My beam size, my beam divergence, actually. So I have to make sure that at the location where the scattering occurs, which is at the interaction point, this ellipse is not too tall. If this ellipse here is too tall, I don't get, because I typically scatter from here. I have to assume I scatter from the center of the beam. I don't get outside the ellipse. I don't get outside my beam. If I don't get outside the ellipse that the beam itself covers, I cannot detect the particle because it will never be outside the beam. Nowhere in the machine. There is no location where I can put my room pods. So that means I have a trade-off between acceptance and luminosity. So you can get more luminosity by squeezing your beam, but that makes this ellipse here taller, and I don't get particles with a small transverse momentum kicked outside that ellipse. Okay, now polarized beam. So this is not directly the interaction region. It has some impact on the interaction region, but I think many people are interested in polarization, so I figured I cover that to some extent. So the physics program requires bunches with both spin directions simultaneously in the machine, in the arcs. The polarization spin direction is up or down. That's why we always refer to them as up or down. At the interaction point, they want them to be longitudinally polarized, but okay, we come to that later. Polarized light ions we can generate at the source, and we have to generate them at the source. There's no way to polarize them once they leave the source. There's no mechanism that polarizes light ions on their way when they are stored in a machine or accelerated. So for electrons, there is an effect that is related to synchrotron radiation again. That's so-called turn-off self-polarization. So that would produce over time polarization in the storage ring that is anti-parallel to the main dipole field. And the growth time for this polarization goes with gamma to the -5. It's a very steep function. At 18 GeV in the EIC, the growth time is about 30 minutes. So if you then go down to 10 or 5 GeV, you realize immediately that this is not the way to polarize the beam. It just takes way too long to polarize it. It also, of course, has the problem that all the bunches would be polarized in the same direction, which is not what the experimenters want to have. So the only way to get these bunch patterns in the EIC electron storage ring is by injecting the bunches with the desired spin direction. And we have to do that at full collision energy, because in a storage ring, if you ramp the energy up, polarization gets lost. One has to play special tricks in a special accelerator to be able to preserve polarization. What happens then is, of course, that Sokolov turnoff is still there, right? The synchrotron radiation still gets emitted, and it wants to reorient all the spins to be anti-parallel to the main dipole field. So you wouldn't end up in the same situation as here. So again, that would destroy your spin patterns that you wanted. And there are also spin diffusion effects that reduce the polarization, but they are almost secondary to this. So what we have to do is we have to frequently replace the bunches. We replace single bunches faster than Sokolov turnoff can turn them in the opposite direction. So at 18 GeV, as I said, Sokolov turnoff time constant is 30 minutes. So if I if I replace my bunches every 2 minutes or so, then that's very short to the 30-minute polarization time that it takes to get them into the opposite direction. So effectively, I can generate bunch patterns both spin up and down in the machine. So this is how that looks like now. This plot here shows basically in a cartoon, the 18 GeV situation. I have bunches from some magic pre-accelerator that I don't want to go into here, that are 85% polarized with positive or negative polarization, which means up or down. And then I inject them, and then of course the polarization decays. And when it reaches some 70% in this case, I kick out that bunch, replace fresh one with 85% polarization. So I get the sawtooth behavior here. For negative polarization, I have to do that faster if I assume that my equilibrium polarization is positive 30%, which is a conservative small number. Basically, that's not a very good machine if it only has a equilibrium polarization of 30%. So this here, of course, the slope is steeper because my equilibrium is further away. That's why I have to do that faster. But on average, I can get average polarizations, time average of 80% with this pattern. So that is how we solve this problem of getting bunch patterns or spin patterns in the electron storage rate. So now, how do we manipulate the spins? So the spin precession in magnetic fields is described by the Thomas PMT equation, right? And here is this omega as a component that belongs to or is governed by transverse magnetic fields and longitudinal magnetic fields. Of course, what this wants to be, so the spins want to be aligned with the magnetic field lines. That's why they are up or down in the dipoles in the arcs of the ring. What this also means here is that if I bend my orbit by an angle phi in a transverse field in a dipole, and the spin will rotate by g times gamma times that same angle. So I can manipulate my spin direction by bending orbits. I can also manipulate the spin direction by longitudinal field solenoids, and that's what we're actually doing. Okay, so now how do we preserve polarization on the ramp? So there are special spin manipulating magnets. They're called Siberian snakes. They were invented in Novosibirsk, that's why they got this name. And so what happens there? A particle travels around the machine once. It samples all kinds of magnetic fields with varying directions that all try to get this the spin direction away from the vertical, so it would eventually depolarize. So now the trick is, and this is really very, very much simplified, after each turn, I flip the spin direction by 180 degrees. So now my particle goes on the next turn, samples the same magnetic fields, but with the opposite spin direction. So the spin manipulation that happened there that I didn't want gets compensated by going through the same procedure basically backwards in a sense. And my polarization is preserved. So my spins do not get tilted away from the vertical. But this is really simplified. In reality, you need several Siberian snakes in a machine, and then it gets complicated. But this is, in a nutshell, an explanation how the Siberian snake works. Okay, another special device in the machine for spin are spin rotators. So the spins are vertical in the arcs, but the experiments want the spins to be longitudinal. So we need to rotate the spins. For hadrons, we use what we have in RIG already. These are helical dipoles that serve as spin rotators. They're not that trivial to explain, basically, not hand waving. For electrons, we use a combination of solenoids and dipoles. So your spin is coming out of the arc, it's vertical, and then it goes through a solenoid of a very well-defined strength. The solenoid then rotates your spin into the radial direction. So it's pointing to the outside of your ring or the inside. Let's say it points to the outside. So it's a 90-degree rotation. And then I have to apply a dipole after that rotates the spin by 90 degrees from radial to longitudinal. And I know that the spin the angle for the spin is G times gamma times the dipole bending angle. And I want that to be 90 degrees, so that gives me my dipole bending angle. So for 18 GeV, that's about 30 milliradian. That I need there to bend the orbit to rotate my spins by 90 degrees. And of course, on the opposite side of the IP, I have to do this whole process in reverse. So again, first dipoles to get to radial and then solenoids to get back to vertical, because vertical is the only stable direction in the arcs. Okay, so now we just look at how this whole thing looks all together. So this is here the hadron storage ring in IR6 in the EIC. And up here, that's the optics. These are the beta functions. You see it's really a tiny, I understand that. So you see in the center here, that's the actual interaction point where the beta is squeezed, where the beam is squeezed to get luminosity. And then we get out there, these high betas here are for the trap cavities. And this is the layout of this whole thing. So this is the interaction point here at 0 along the x-axis. The hadrons come from the left. So they go through a spin rotator here, then trap cavities. These are the focusing elements. They get focused to tiny beam sizes, and they get sort of defocused, you could say, back to regular large beam sizes. The grabbing is reversed, the spin rotator to get the spin back into vertical. And so that's how this thing looks. And of course, I'm also showing here showing you other elements. This is here approximately the electron beam path here dashed through that. So the next slide shows the electron interaction region, which looks sort of similar. So now we come from the upper right here, going through spin rotators and trap cavities, focus again to the IP. We have focusing elements on the outgoing side. We have a luminosity monitor here and E-taggers. And then we have to uncrab and get the spin back to vertical. Okay, and that is it. And I stayed in my time. Wow. So I think I gave you an idea that the EIC is a really highly complex collider. It is honestly much more complex than, for example, the LHC, because we have different particle species, electrons and hadrons in the machine at the same time. We have crab crossing, we have polarization, so it's much more complex than that. And the interaction region of this machine has to fulfill many requirements. High luminosity beams have to be separated, the acceptance for low PT particles, and longitudinal polarization. And I hope you got a flavor that interaction region design is always a compromise between all these requirements. There is no perfect interaction region. And for example, I showed you two things that you have to balance. It's the transverse PT acceptance and luminosity. You can't have it both. So, and one has to negotiate what one wants. All right, any questions?
Yes. And again, since we don't have the discussion section, we have plenty of time for questions, so appreciate it. So,
Yes.
What are in the last two slides before this? Can you just say what the labels for the axes are? Because I can't see it when I zoom in on the PowerPoint.
That's on what slide?
This one and the one before, just on the two plots.
Okay. So in X, that's the longitudinal position in meters. This is the transverse position in meters. So this is highly distorted, right? I mean, if you plot this with equal axes, then you see a straight line.
Okay. Thank you.
And it's the same on the other plot as well. Yes.
Can the beams also be transversely polarized? The interaction region or just longitudinal?
Oh, they can be transversely polarized. Oh, yes, if you don't do anything, they are vertically polarized. And they can also be, I mean, to do that, radially polarized. We actually did that once in rig by accident. In the very beginning, in the first year, we set the rotators wrong. And yes, the experimenters came, oh, great, yes, you rotated your spin by 90 degrees, but in the wrong direction. Else? Yes.
What are the Siberian snakes? That you mentioned Siberian snakes.
Ah.
I never heard of that.
Yeah, okay. So the simplest version of Siberian snake is a solenoid, right? Your spin enters vertically, and you set your solenoid strength, your integrated strength, such that it gets rotated by 180 degrees. That's the simplest version, and then there are more complicated versions because in reality, if you have multiple Siberian snakes in the machine, the orientation of the rotation axis matters. You don't just go from up to down, you have to go around an axis that is at 45 degrees relative to the orbit, for example. So it's not that simple, but the simplest version is just a solenoid. Think of a single Siberian snake. And of course, the more complicated ones, they get funny orbits. That's why they have the name.
So for the polarization, for polarizing the beam, are you using microwaves or like any other method? And also the next thing is to measure the polarization, is it some NMR system that you are using, or you are using the
To measure the polarization, we use convex scattering. You shoot a laser against the beam, and then you get an asymmetry depending on polarization. And to generate polarized beams, the beam is generated at a photocathode. You shoot a laser onto a cathode, and the cathode is this magic material. It's basically a strained crystal. So you have a crystal, and the last layers are a different material, so they don't get basically the lattice size in the crystal that they would get if that was solid crystal. And if you now shoot your laser onto that, the electrons are polarized that come out of that. So that's some, I don't know the details, but that's some very interesting, sophisticated physics. Yes.
All right, well, let's thank Christoph again and. Break for lunch. Let's start again at 1:30. So have a good lunch and we'll see you then.
There's some plans to use energy recovering capabilities for the electrons. I've heard of those recently. It's possible I see it.
Okay, so there was a concept until 9 years ago to do it that way for the electrons, and it was